Hello, I think we should start. Peter introduced me, but again I'm Bon Chubonev. I'm associated professor here in Technical University of Sofia, Department of Radio Communication and Video Technologies, and I teach radio wave propagation, also wireless optical communications, and some other subjects. So today we will be together here in this course. We have some topics today. The first one is radio wave propagation, main principles, phenomena and equations. Then second part is ionosphere. Third part is troposphere, and the final one is propagation characteristics and application of radio waves of frequency, different frequency bands. So, as Peter said to me, some of you are not familiar with wave propagation, but some here first two rows are my students, so I will try to explain more physically things and less mathematically. If you have some questions, you could interrupt me and ask. And I think that's all. If you have something to ask in the beginning or to start. Okay. First subject is radio wave propagation, main principles, phenomena and equations. As you maybe know, in the fundamental for electromagnetism is are Maxwell equations. He summarized in 1873 the results got by other researchers like Ampere, Faraday, and formulated four main equations called Maxwell's equations. And as I said, this is fundamental equations for electromagnetism, for wave propagation, for antennas, and for everything that's part of electromagnetism. What are key points of electromagnetic wave production? I don't write here Maxwell equations because that I said previously about mathematics. But from Maxwell equations, we could conclude that time-varying magnetic field can produce electric field. Electromagnetic field has two components, electric field and magnetic field. These two fields are connected, and from these equations and from researches of these researchers, Ampere, Faraday, and others, they concluded that variation of magnetic field produce electric field. Producing electric field is variation of electric field. and this produces again magnetic field. And in this way, electromagnetic field propagates in the space. One field, electric, when it changes, produce other. Producing of other is change of this field, and this again produces the first one, and in this way it propagates in the space. So the first one I said is Faraday's law. Changing magnetic fields can induce an electric field, and the second one is Maxwell's idea that changing of electric field can also induce a magnetic field. Tomorrow we will see that there is also one other thing that can produce magnetic field, and that is current in some wire, and this is fundamental for antenna radiation. When you have current in some wire, and this current changes in time, this also produces magnetic field, and then production of magnetic field produce electric, etc. So this is fundamental for radio wave propagation. Maxwell equation, and these two things that changing of one field produce another one. So electromagnetic wave has two components: electric component. Here in this figure, it is with red color, and magnetic component with blue one. Electric field and magnetic field for electromagnetic waves that propagates in the space are perpendicular each other. In this case, we have transverse wave, so the two components, E and here this is B, are perpendicular to direction of propagation. This is direction of propagation, z-axis. On x axis there is electric field, and B is oriented on y axis. So these two fields are perpendicular each other, and they are perpendicular to propagation direction. In the next slide is given main principle of electromagnetic wave radiation. Here we have antenna, wire antenna, and in this antenna we have some current that is you don't see. Okay, I see here.
Yeah, the point, but here is
the point, but here is no point. Okay, I will explain it here. We have wire antenna, and current in this antenna is I. This current is not constant, it changes in time. So in the first moment, this is the direction of the current, and this is electric field with red lines, and this is magnetic field. In this case, it is oriented to the wall in this way. So, in second moment, when current changes in direction, and this is direction, in this case, this is electric lines from plus to minus, and this is magnetic field. But changes in this of electric and magnetic fields in this part of the space produce another field, and radio waves start to propagate in the space in this way. And in distance far away from the transmitter, this is electric field in one semi-period, and this is in other semi-period. So this is magnetic field lines with blue.
This would be a radio wave because of the frequency that we switch the current, right?
Yes, when current switch polarity, we have electromagnetic wave radiation. If we have constant current, we will have electromagnetic field around this wire, but there is not radio waves, there is not electromagnetic waves, only electromagnetic field, and it will be smaller and smaller and smaller with distance, and only that. But if we have changes, tomorrow Peter will explain this. This is my principle of electromagnetic wave radiation. You need changes of current to produce waves.
The frequency of change of current will be equal to the frequency of the wave.
Yes, the frequency of change of current is equal to the frequency of the wave. And the frequency will not change with propagation. There is one Doppler effect that is, but we will explain this. It is not change, global change of frequency, but this is frequency shift because of movement of a transmitter or a receiver. But other parameters like wavelength could change in the in space or in other medium because of electric and magnetic parameters of the medium. So this is one very important parameter of radio waves and electromagnetic waves. This is velocity of electromagnetic waves. There are two velocities. The first one is phase velocity, this one. So some things about these two velocities. We have different type of mediums. in some mediums, for example, like air, electromagnetic parameters of medium is the same for each frequency. So it not change with frequency. So these mediums are not dispersive, non-dispersive mediums. And there are other which parameters change with frequency. For one frequency we have one value of parameter, for other frequency we have different value of the parameter. For example, water is like this, ionosphere also, ionized molecules. So in these mediums that is dispersive, we need to define two velocities, phase and group velocity. Phase velocity and group velocity in non-dispersive medium are equal each other. So we, in this case, we speak about the velocity of, or speed of electromagnetic wave. And this is phase velocity in air, for example, and in vacuum, it is equal to 1 over square root of epsilon 0 mu 0. This is permeability or permittivity of vacuum. This is values of these two, and this is equal to 3 multiplied by 10 on 8 meter per second. So this is speed of light. You know, light is also electromagnetic wave, as you know. So the speed of radio waves and the speed of light are equal. In this case, we could see free space, vacuum or air. So this is phase velocity. And if we have non-dispersive medium, this speed or this velocity is equal to another one, that is group velocity. If we have dispersive medium, these parameters of medium for different frequencies will be different. So for one frequency we will have one velocity, for other frequency we will have other velocity. So different spectrum components of the signal will propagate with different phase velocity. And in this case we need to define another velocity, group velocity, that is velocity of the whole signal. Something of signals, and we have this electromagnetic wave, and this electromagnetic wave is modulated with another low frequency signal. This is amplitude modulation. Amplitude of electromagnetic wave depends on this low frequency signal. So the speed of propagation of this electromagnetic wave is phase velocity, and the speed of propagation of this curve is group velocity. I hope this will be better. You could see in this case group velocity bigger than phase velocity. The blue curve propagates with lower speed or lower velocity than red one. In this case, we have equal velocities, group and phase. This is for non-dispersive medium. This is not usual for radio wave propagation. Group velocity to be higher than phase velocity. And this is the case in dispersive medium from radio wave propagation. You could see the blue curve propagates with high speed than red one. So there is something very important. Power and information propagates with group velocity. The velocity of propagation of a red line is velocity of energy propagation. So something that is very interesting, that phase velocity in some mediums could be bigger than speed of light. Speed of light. Phase velocity. This is not velocity of propagation of information or energy. This is velocity of movement of the phase of electromagnetic wave, not velocity of energy propagation. So there is nothing that is not okay. Group velocity is every time smaller or equal to speed of light. In ionosphere, phase velocity is bigger than speed of light. Also, in rectangular waveguide, some of you know this. In this case, also phase velocity is bigger than speed of light, but group velocity in this case is smaller. In these cases, we would write that phase velocity multiplied by group velocity is equal to speed of light square of speed of light. So if this one is bigger than speed of light, other one is smaller in dispersive medium. In non-dispersive medium, in more cases, they are equal to speed of light. So, it is clear. Okay. Wave rate. This is wave propagates on z direction. So distance between two max or two means or two zeros or these two zeros, but in this case we have from negative to positive, and here also same phase states. Distance between two equal phase states is wavelength. This is Greek letter lambda, and wavelength is equal to phase velocity over frequency. So because phase velocity could be different in different mediums, wavelength could be different in different mediums, but frequency is the same. For example, in the Earth, phase velocity is different, it is smaller, and therefore wavelength is also smaller than in the air. But frequency is the same. So this is wavelength. And other very important characteristic of electromagnetic wave or radio wave, it is polarization. So, as I said previously, electric and magnetic fields are perpendicular each other, and they are perpendicular to propagation direction. In this case, we have transverse electromagnetic wave or TEM wave. A radio wave propagates in free space are TEM waves. In waveguides, we have different type of waves. Tomorrow, maybe you will learn about that. So, wave polarization is determinant of direction of electric field vector. So we have electric field and magnetic field, and this is propagation direction, x and z. Direction of electric field gives us type of polarization. We have two main types of polarization: linear and elliptical or circular polarization. If I could see electric field and I'm on the place of transmitter, if one radio wave propagates in this direction, I see one line. This is linear polarization. So B is every time in one plane. It propagates. When a radio wave propagates, electric field is in one plane, only in this plane. This plane not change, no. when radio wave propagates. In second case, elliptical polarization, if we have the same example, I'm in the transmitter point and I see the E, I will see one ellipse. Or if you have circular polarization, one circle. This is, or E vector will rotate over propagation axis. And this point will describe one circle. So this is circular polarization. Linear polarization is two types, vertical or horizontal. in practical cases. When E vector is vertical or it propagates in vertical plane, we have vertical polarization. Where electric field vector is parallel to the ground surface, we have horizontal polarization. It could be also not vertical or horizontal, but every time it will have one vertical component and one horizontal. If this is E, this is vertical component and this is horizontal component. So we use these two directions, horizontal and vertical, to define polarization when it is linear. So circular polarization or elliptical, this is elliptical, this is circular. When electric field vector rotates on left hand, right direction, we have right directional polarization, in left direction polarization. But the point of view is transmitter, because if you try to see the same thing from the transmitter is the point of view. If you want to see the same from the receiver's point, it will be opposite. So you are in the point of transmitter. If electric field vector rotates in right direction, this is right directional polarization. If it rotates in left direction, it is left directional polarization. There is one very important thing. If you have a right direction polarization of electromagnetic wave, you need a receiver's antenna with a right directional polarization to receive this signal. If you have left directional antenna, you will receive nothing. The same is with horizontal or vertical polarization. If your wave is with vertical polarization and your receiver's antenna is for horizontal polarization, the receiver signal will be zero or almost zero. This is very important and I think very good, because you could use one frequency two times. One time with one polarization, other time with other polarization on same link. It is not usual, but almost the same frequencies. And in the receiver, you could receive one signal with horizontal, one signal with vertical polarization, or one signal with right directional and one signal with left directional polarization.
If we have a linear polarization and our signal is not like in line, we're just going to catch the component, right? If we're in X, let's say our polarizer is in X direction, and we have a wave that is linearly polarized and coming in an angle towards X, we're just going to catch the X component, like there, right?
Here,
Yes.
here you will use antenna that is with same direction, that is E. Or to use two antennas for horizontal and for vertical, and then to sum to 8 one signal to another.
Yeah, that's the optimal. But let's say it's not an ideal situation and we're catching a signal that's linearly polarized but not in line. We're just going to catch its x component or whatever direction we are in.
It would be like projecting the vector of the direction of
Yes. That was my idea. But
you have depolarized signal, and its polarization is with different direction in different time. Or
no, it's constant. I was just going to our next point. So if we have a linear polarization, it's straightforward. We're just going to catch the x component. So signal comes in like this, we have our polarizer like this, so we're catching only this component.
yes.
Okay. What about the circular polarization? It's either left or right.
Circular.
Yeah, so can we catch a component in it or no?
If you use linear polarization,
No. You said if you have
if you have circular polarization, you will receive almost zero. There is impossible.
so we can't split it into components like we could with the
No. In circular polarization, that is good for circular polarization because there is not cross polarization.
Okay.
And also one very important thing, if you have circular polarization, when this wave are reflected from some surface, it changes direction of polarization, and in the receiver you could not receive reflected wave, only direct wave. You need two reflections to receive a reflected wave, and if you have two reflections, the amplitude will be very small because 2 times.
If you do want to do interferometry, that would be good. If you want to do interferometry, that would be good, I guess.
So. We are okay with first part of this lecture, and second part of first subject. We will start with frequency bands. Now we will define only frequency and wavelength, and at the end we will say something about propagation characteristic and applications, but at the end of the day, not at the end of this lecture. So, we will start with extremely low frequency. 3 to 30 hertz, and this is wavelength. Then super low frequency, if you see frequency increase with 1 order, and this decrease with 1. Then ultra low, and these 3 bands are not used for communication, because frequency band is very short, and if we need to transmit some data, we need spectrum. But here we have very, very small spectrum, and therefore this is impossible to transmit data, or if we transmit data, it will be with very slow. It is used, for example, for communication with underwater communication, because in the water attenuation of radio waves with high frequencies are very high, and therefore we need to use very small frequencies to communicate with objects that are underwater. But that is only application of this. So, very low frequency, and this is from 3 kHz to 30 kHz. Here we could transmit some data, but with very slow speed also. Then here, from low frequency to extremely high frequency, are frequency bands that are used for communications. Low frequency from 30 kHz to 300 kHz. These low frequencies are used for radio broadcasting with amplitude modulation, but now here in Bulgaria we don't have LF radio broadcasting. I think only in some big countries is used a low frequency for broadcasting, because it propagates on very long distances, and it is not usual to use in small countries like Bulgaria. Then medium frequency from 300 kHz to 3 MHz. It is used. It is used also for radio broadcasting with amplitude modulation. In the past, it was maybe most used frequency band for radio broadcasting in the past, maybe in 50s of previous century. But now it is used only for places where other frequencies don't propagate well, and we have not signal coverage with VHF signal. So, high frequency is the next band from 3 to 30 MHz. Very high frequency from 30 to 300 MHz. Here we have radio broadcasting with frequency modulation with high quality, and then we have ultra high frequencies from 300 MHz to 3 GHz. This is maybe most used frequency band in communications now. Here we have also TV broadcasting, 3G, 2G, 3, 4, 5. Then we have super high frequencies from 3 to 30 gigahertz. This is also frequency band that is used in communications, but in more cases not for application that everyone use, but for telecommunication operators applications. For example, to transmit data from one point to other point, from base station to a base controller or something like this. Also, this is the frequency band for satellite communication. Extremely high frequency. In last years, this is more and more used frequency band because we have very wide frequency band, very wide spectrum, and we could transfer very data with very high speed. So in the future, maybe this will be the most useful frequency band. Here we will work some of 6G, 6th generation communication, and also another high-speed communication. And the last one is terahertz on tremendously high frequency band. It is almost not used in communication because attenuation in Earth atmosphere is extremely high. For some matters, almost everything attenuate in the atmosphere. Very high attenuation.
For radio astronomy, wouldn't we be looking at the first three? Those elves?
Maybe here. In next subject, when we learn about ionosphere, we will see that this frequency band to high frequency and a little very high frequency refract from ionosphere. And if you have signal from the space, it will refract from ionosphere, from the upper ionosphere, and it will returns again to the space. Only if it incident to the ionosphere in very high angle, it has it could pass the ionosphere and could reach the Earth surface. Only if angle is very high.
Like perpendicular.
Perpendicular.
Oh. Okay.
In next chapter we will see this. So high frequency and here maybe to super high frequency. Because here extremely high frequencies we have very high attenuation in the atmosphere, and the situation is almost the same. This low frequency, this is okay, but low, medium is absolutely important, absolutely impossible. because they repent and returns to the space again. Electromagnetic wave propagation in the free space. What is free space? We define free space as space where objects and medium don't influence radio wave propagation, but not vacuum, not only vacuum. In this free space, propagation medium doesn't affect radio wave propagation. So, in propagation of electromagnetic wave, only very small part of transmitted power reach the receiver. Why? First is this phenomenon, natural scattering of energy. I will explain it. And second one is influence of propagation medium. In free space, this is so natural scatter of energy. Here is transmitter. It propagates spherical wave. It propagates in all directions. So, in given moment, this is wavefront. One sphere with radius d. One. Small sphere. And power, transmitted power, is distributed on this sphere. In second moment, this is wavefront. Also sphere, but with bigger radius, with bigger surface, and therefore power density is small. If you throw a stone in the water, close to the place you throw the stone, the waves are bigger, and when they propagate in the water, they are smaller and smaller and smaller, and in the one moment we have no waves. So this is the same in radio waves, but in 3D space, 3-directional space. So, when propagation medium influences electromagnetic wave, we could have absorption, obstacles, interference, and depolarization. And because of this, radio wave attenuates and smaller part of transmitted power reach the receiver. So we have two components. This one is natural component. It is impossible to compensate. Almost impossible to compensate this, but this one is we could use frequencies where there is not absorption, to change antenna heads, and in this case we could use obstacles to gain the signal also. You could see in the next part, etc. So this is main propagation relations. In free space, this is power. P is power of transmitter. This is antenna gain. And this is distance. This is electric field. And this is received power. PT is transmitted power, gain of transmitter's antenna, receiver's antenna. This is wavelength, and here I used R for distance. In low frequencies, about 300 MHz, we use this formula. For frequencies higher than 300 MHz, we use this formula. Why? Because for low frequencies, the gain of receiver's antenna is relatively small. But for high frequencies, the gain of receiver's antenna is very high. And in these cases, our received signal will depends on gain of receiver's antenna, because these gains could be from around 50,000 to 100,000 times. What is antenna gain? We will try to explain. So we have one antenna that is called isotropic antenna. Isotropic antenna propagates in the same way in all directions. So the radiation pattern will be a sphere with radius 1. This is isotropic antenna. In practice, we don't have isotropic antennas. We have directional antennas. And this directional antenna has such a radiation pattern. If we integrate radiated power on this volume and on this volume, it will be they will be equal. So we radiate the same power in this case and in this case. But if we have receiver here and here, in this case, more of power is directed to the receiver. In this case, I could place the receiver in different points and the received signal will be the same. But in this case, in this direction, this antenna transmitted? No. So this is antenna gain. Tomorrow, Peter will explain more details about this, because we have directivity of antennas and gain of antennas. Today we will say that this is gain. So this isotropic antenna has gain that is 1, and this directional antenna has gain that is bigger than gain of isotropical antenna, or bigger than 1. And that is antenna gain. Antenna how to say, concentrate power in some direction. In these directions, it transmits smaller part of power according to this situation. And in this direction, we have main part of transmitted power.
Is it fair to say that the gain is a relation between an homogeneous isotropic antenna that is sending out everywhere to the one that we have directional? So,
Okay.
or in other words, how much we gain from the shape of the antenna compared to?
Okay,
if it was
you explain. Here, let me have isotropic antenna, and transmitted power is Pi. And in this case, on some distance, D, we have some field. In this case, we use another power, P. And here, we have the same, at the same distance, we have the same electric field. Antenna gain is equal to this power over this power. In this case, we will use smaller power, and we will have the same electric field. One very interesting example, if we use, for example, parabolic antenna, such antenna we use for satellite communication, and antenna diameter is 3 meters, and frequency is 10 gigahertz. That means antenna gain will be 70,000 times. We have 2 antennas with 70,000 times gain. This is 5 billion times when we multiply each other. So if we use isotropic antennas, we could use, for example, 5 billion times bigger power than in other case. This is almost one nuclear center. If in this case, with 3 meters antenna, we use 1 watt power. In this case, with isotropic antennas, we have to use 5 billion watts power, and we will receive the same power in the receiver in two cases. This is impossible to use such power because we don't need.
Can I ask a question?
Yes.
So I noticed that we have two G's in the formula. So one is for the receiver and one is for the sender.
Yes. This is with T for the transmitter and with R for the receiver. And PT and PR are transmitted power and received power. So this one is 1 over LFS of free space losses.
Free space.
Yes. Okay. Why we have free space losses? It is free space, but we have losses. This is free space losses because of natural scattering of energy.
But why is it proportional to 1 to the?
Yes, this
It's
is.
not free space?
This is also free space losses because D is here and here distance is R and it is also here. With distance, received power decrease.
Yeah, but why there's lambda? Why there's the?
Because antenna parameters depends on lambda. Receiver's antenna parameters, and therefore we have lambda in received power. In depends on wavelength. So for high frequencies, the free space losses are higher for high frequencies. For example, if you have 1 gigahertz and 10 gigahertz, in second case, for 10 gigahertz, we will have 100 times bigger free space losses, or signal level power, signal power, received power will be 100 times smaller than in case of 1 gigahertz. And therefore, for long distances, we use smaller frequencies. Yes, there is also one very important thing. If you have high frequency with antenna, for example, 1 meter in diameter, for 1 gigahertz you will have smaller antenna gain, but with 1 meter in diameter antenna for 10 gigahertz we will have bigger antenna gain. So it compensates with antenna gain.
With the diameter of the antenna.
Same diameter, but antenna gain is different. So therefore we have here lambda. This is in free space. Only free space losses or natural scatter of energy. In real medium, we have additional losses because of absorption obstacles, etc. So in this case, we add here one coefficient
The medium.
F. It is equal to electrical field in real conditions over electrical field in free space. And now we will explain how to calculate this parameter in different cases, when we have obstacles, when we have interference, etc. This is the only difference between free space and real method. This additional coefficient. And if you see here, it is equal to this over this on E real is E free space multiplied by F. Here, this is E free space multiplied by F. Because this is complex coefficient, we will use only its real part. Absolute. So, here in power, we multiply it by such a coefficient on square. Because power depends on square of intensity. Obstacles. We have two antennas, and here we have obstacle. This is H. Here is another quantity, and this is figure. From which we could obtain this coefficient F. It depends on this distance, and there is one very interesting thing. Here, this coefficient is bigger than 1. Or when we have obstacle, the obstacle could gain the signal in the receiver. Very strange, but it is true. If you want, my lab is here, then in the some of breaks we could come there and I could demonstrate this. If we move antenna on A and reach this point, when we have obstacle, the signal is bigger than when we remove obstacle. Or obstacle.
But this is because of the interference of the.
This is because of diffraction.
Yes, diffraction.
Here,
The obstacle becomes a source, and when they are in
no. Because we don't have enough time, didn't include diffraction theory, Fresnel zone theory in the presentation. But you maybe know something about this, some of you. This is first Fresnel zone. This is second. This is third, etc. This is obstacle. So the waves from third Fresnel zone increase the signal level in the transmitter. If I move obstacle up and down, up in this case, I will close part of these waves that give us increase of signal in the receiver. And our signal will decrease here. Then I start to move and to hide second Fresnel zone. In this case, I eliminate these waves that give us increase of field, decrease of field. Second Fresnel zone are with opposite phase than first and third Fresnel zone. And here, in second Fresnel zone, electric field decrease, but I hide this part of second Fresnel zone, and we have increase. And in this part, when I continue to hide this picture, we
because
get this part of figure. So in this case, how much will be F when line of sight is over the obstacle head? How much will be F in this case when V is 0? 0.5, because half of picture is height, or half of power is blocked.
because the energy is
That is explanation.
But physically, it's because the edge of the obstacle is also becoming a source, and the received wave is a sum of this, of the original wave, plus the one that is.
This is one of theory that when you calculate the received power, you assume that there are a second source here. But this is maybe not explanation, but a way to calculate the power. Maybe, because this is a theory of diffraction. Huygens principle that because there are also theory about 2 or 3 obstacles, and then you calculate for bigger one, then if between this and this, and here you have one more, you assume that this is the height of the second transmitter, and but this is very complex, and I think it is not for here. So phenomenon is interference. We have interference when in the receiver we have more than one wave. For example, if you have transmitter and receiver and the Earth surface between them reflects electromagnetic waves, you will have one direct wave and one reflected wave. And in this case, the electric field is sum of two fields for directed wave and reflected wave. But this is vector sum. And also this is sum of complex quantities. So in this case we have to take attention about amplitude and phase of these two waves. So this is figure of A depends on distance r. If we have only direct wave, this is dependence. With distance, electric field decreases because of scattering of energy. But if we have direct and reflected wave, in one case, these two waves are in the same phase. Or in this case, we will add reflected wave to direct one. And our intensity of electric field will be bigger. In other case, these two will have opposite signs. One with plus, other with minus. And we will have mean. And for very big distances, you could see that electric field is smaller than if we have only direct wave. Because in this case, for big distances, angle of excidence this angle will be very small if distance is big, and therefore reflection coefficient will be almost 1, and when electromagnetic wave reflects from some surface, we have change of amplitude. This gives us information about amplitude change, but also phase changes. And we have another parameter that gives us information about phase change. And in this case, when this angle is very small, for horizontal polarization, this angle is almost 180 degrees. Or what we have? We have two waves with almost the same amplitude, because reflection coefficient is 1. Because of big distance, this is part of reflection wave. This is part of direct wave. If we increase the distance, these two parts will be almost the same, I think. Because they will be close, almost the same parts. And therefore, the amplitudes will be the same of these two waves. Because parts are the same, and also reflection coefficient is 1. But
The phase is opposite.
the phase is opposite of reflected wave. And therefore, we have E direct minus E reflected. And because of the same amplitude, we have intensity almost 0 in this case. For vertical polarization, this is close to 0 in most cases where distance is very high. And that means that it will be higher than intensity for directed wave. Or when we have strong reflected wave, we could use which polarization? Horizontal or vertical? Vertical. If we have circular polarization, we will receive only directed, because rotation will change, direction of rotation will change in reflection, and if direct wave is with right directional circular polarization, this one will be with left direction, this one, if this is propagation direction, and therefore here receiver will receive only direct wave. Or the best is circular polarization, then vertical, and then horizontal. Why I said that circular is the best but not vertical? Because we will see then that it could change. This is distance. If we have some radial link, we have fixed distance, and this is, for example, our electric field in the receiver. But because of troposphere refraction, we will see this in next lecture. This picture will move around transmitter, and in some case, maybe this point mean will be in the receiver point. And it's better to have something that is constant, but not something that is bigger, but in other time it is smaller and maybe 0. This is electrical field dependence of receiver's antenna height. Almost the same means at max, and here if we place our antenna in this point, in this case, we will have max, but when it starts to move, this mean could move here, and we will receive that or not. In this case, what we do?
Change polarization.
We place one antenna here, in this point, and I will place one other antenna here. And when this starts to move, if this move here, this will move here.
Yeah.
And in this case, I will compare two signals,
Yeah.
and we will take the bigger one. And one of them will be with level bigger than some average level.
And this distance between the two antennas will be proportional to the wavelength, or no? The distance between the two antennas.
The distance between two antennas is
Is it related to the wavelength?
yes, that one plus half of that one, or 1.5 multiplied by that one.
The wavelength.
No, this is not wavelength. This is period of this dependence.
Okay, but if
Because
this
this is-
dependence related to the wavelength, I mean, would it look different if I'm doing a different wavelength? This distance would be
Yes,
different?
it depends of wavelength, but in this case, this is period of this dependence. If you have some signal with some spectrum, it will be not the same for all frequencies, but you will have very big difference between two frequencies to move this mean in the this point. This is called spatial diversity. You have two antennas in different places, and you choose the bigger signal. There are also frequency diversity. You could, if this reflection depends on frequency, very strong, you could use two frequencies in one link. And if with the same antenna height, same antenna, you transmit signal on two frequencies and receive the signal on two frequencies. But you, for one frequency, in this case, you have to have max, and for other frequency, for such height, you have to have mean of this graph. So, two signals have to be independent. I will give you an example. This is not with reflection, but this is frequency diversity. Optical waves attenuate very strong in fog. And therefore, if you have one link in optical band, if you have heavy fog, the link will interrupt. What we have to do in this case? We could use on same points one radio link. Fog doesn't affect radio waves. So if we have fog, radio link will operate and we will transmit information on radio link. But radio waves attenuate in rain. And when we have heavy rain, maybe radio link will interrupt. But rain doesn't affect optical links. And in this case, optical link will operate. So if we have rain, optical link will operate. If we have fog, radio link will operate. But heavy rain and heavy fog in the same time is almost impossible, only possible. So one of them will operate in everything. This is frequency diversity, and this is spatial diversity. When we have in two different points antennas. So for these two things we will talk later, but I want to say something about first we have, I think, maybe 10 more minutes. No, 4. Depolarization. What is depolarization? This is change of direction of electric field vector when radio wave propagates, and these changes are sporadic, because one of things that affect polarization direction, this is ionosphere. In ionosphere, we have phenomena that are stochastic, and we don't know what will change in ionosphere in given time, and therefore the electric field direction changes with time. And if we transmit the signal with vertical polarization, for example, after it propagates in ionosphere, it will be with horizontal and with some band polarization. And we don't know the polarization direction. In rain, also, this is very interesting, and we will talk about this when we talk about rain absorption. But raindrops absorb radio waves, and because size of raindrops are different in vertical and horizontal direction, this absorption is different. And if we have ground to space link, it is not pure horizontal or pure vertical polarization. Electrical field is perpendicular to polarization direction, to propagation direction, and it is impossible to be purely vertical. It will be with some bend over horizon. So it will have horizontal and vertical component, and these two components will have different absorption rate. So one component will decrease smaller, other will decrease bigger. And if we sum after the rain, the polarization direction will be different. Here is, this is E, and this is two components, or vertical and horizontal. For example, this is half of this one, and this is 70% of original. with some, in this case, after the rain, electric field direction will be different. And this is depolarization. And this is stochastic because we don't know when we will have the rain. The wind also change the direction and the size of raindrops. And therefore, we don't know in this case what will be the polarization. And therefore, it is impossible to use the same frequency with horizontal and vertical polarization on the same link. I said that it is good because if you have horizontal polarization, it doesn't affect vertical, but if we have depolarization, it is not. So this is also depolarization, and we will talk about absorption too in next chapter. So I think it's time to break.